I don't know if you know you're muted.
Okay, hello everybody. Can you hear me?
Yep.
Yeah, I can hear you.
Yeah, we can hear you.
Okay, how you doing? Are you already at home and enjoying
Not just yet.
sunshine? Not just
I'm in
yet.
STEM.
Okay. All right. So I got still 3 people waiting, but wow, yeah, it's pretty high attendance. That's pretty good. Okay. So let's begin today. I'm going to begin with updates. Okay. So there are 2 new updates right here. I hope you're seeing my desktop. All right. So this is an announcement made on Sunday, November 21. Let me just mute everybody for a moment, okay? So if you have any question, just unmute yourself anytime, okay? All right. So first of all, here is just the end of the semester plan, all the due dates, which is given here. So right after the Thanksgiving week, okay? Wednesday, December 1st, homework B4 and also quiz 7. Quiz 7 is something new added here, so don't forget. So if you click on quiz 7 right here, you see, okay, you see an equation you've seen before. This is coming all the way from Unit A5. Like I said, Unit A5 equation is quite important. You're going to integrate from leading edge to trailing edge, pressure distribution and shear stress distribution over the surface to determine normal and actual force, and then moment, in this case, leading edge moment. And then you can determine lift and drag based on the angle of attack. That's what we did. And then we applied for a flow of a circular cylinder, okay? You have to take a look at, well, this big hint, okay? Take a look at handout B3B and handout B4B. Those are handouts, okay? Take a look at those handouts. Handouts B3B, B4B is just application of this equation coming from Unit A5, page 5, applied to the situation of the flow of a circular cylinder with and without spin. Okay. Now you are going to develop your equation, which can be applied for the flow over an airfoil. Okay. So this is a flow over an airfoil. I keep having this thing. I don't know what it is. Okay. All right. So flow over an airfoil. So this is leading edge. Okay. Anyways, this is trailing edge. So obviously over the surface, pressure and shear stress distributes over. And then you're going to integrate from leading edge to trailing edge to determine what is the CL. This is super important equation. You're going to use it. Okay, after you run wind tunnel testing like this, you're going to determine CL based on at least the pressure distribution over the surface. This is going to happen next semester also when you start taking wind tunnel testing class. Okay, so please do this. This is the last quiz of the semester. Do all the mathematical derivation to get lift coefficient out of those distributed pressure and shear stress over the surface. You're integrating mathematically from leading edge to trailing edge to determine lift coefficient per unit span. Any question about this quiz? This is due right after Thanksgiving, the Friday. Okay? And then, no, not the Friday, sorry, Wednesday. Okay. Friday, December 3rd, okay, project 2B is due. And then at the same time as you submit project 2B, you're going to form up your team for project 3A and 3B. Start working on it. Actually, you don't have to wait for this Friday, December 3rd to start working on project 3 if you're really motivated and interested in using X-Flyer 5. This is all about panel method. I can't write anything. Oh, okay, sorry. This is web page. Sorry about that. So this is all about X-Flyer 5 panel method. So you can start working on it by taking a look at it. Lecture notes of Unit C3. This is YouTube lecture of panel method. Okay. And then project 3A is very simple. You are going to self-run by yourself what it is and how to use it. Okay. And try to understand what is panel method to begin with. And based off of that, you're going to work on project 3B, which is a very introductory practice of using X-Flyer 5, which is due, this is the study day, right? Friday, December 10th, study day. I'm going to wait until midnight on Friday, okay? Basically, this is the day officially the semester ends. So Saturday, no, I cannot stretch it because Saturday is considered to be a final exam week. I cannot cover any material, okay? So this is absolute deadline, okay? Midnight on Friday. Too bad, okay? Then after midnight on Friday, you cannot even access to the campus. I'm going to close your access to campus, okay? And then Wednesday, December 8th, you're going to turn in homework C2 and C3 both. Monday, project 3A. Yeah, 3A is, like I said, it's very simple self-learning of how to use panel method, what it is, and some basic things, okay, of X-Flyer 5. Homework C1 is due Monday. Do you have any question about those schedule? obviously, there's not much room to negotiate, but please do your best. Today is what, Monday 22nd, right? Okay, so please plan ahead. You still have time. Okay, any question? There's not much room to negotiate. Okay, so please plan for it. Go ahead, Zach. You're raising hand.
Yeah, I've a question. I don't know. Can you hear me?
Yeah, I can hear.
Awesome. You talked about panel method and that xFlyer 5, that's what it uses. I'm wondering what other methods there are that are used, or is that pretty much it?
Okay, so xY5 is basically this one, panel method, okay, node C3, right? And also boundary layer added on. So unit D2 is optional reference. I'm not going to, probably, I don't have time to cover it, but this is essentially boundary layer theory. This unit D2 talks about flat plate boundary layer, how does it develop and how does it transition from laminar to turbulent. Now, once you know how it behaves over the flat plate, next thing is you are going to apply the same theory for just the curved path. Curved path really means that you have you added pressure gradient, either positive or negative, adverse or favorable pressure gradient. So it is going to actually change the behavior of the boundary layer. So that is actually added on top of panel method. That's xFlyer 5.
Got it. Thank you.
And also one thing, okay, one more thing, which we're going to cover that later, but in unit D1, we are going to talk about high-speed flow, which is more than 0.3 Mach number. Obviously, the compressibility starts to kick in, okay? It's this here. No, it's not here. Sorry. It's unit C2. Yeah, that's right. Sorry about that. So unit C2, yeah, compressibility kicks in. And then we're going to talk about that a little bit later. But here, Prandtl-Grauert correction, which is for more than 0.3 Mach number, you are going to consider the changing density. This is the equation to correct that CP value. So if you turn on check mark on xFlyer 5 of using more than 0.3 Mach number, you are going to automatically turn on this equation, Prandtl-Grauert correction equation. Okay, this is something added on to. So xFlyer 5 is panel method press, compressibility correction based on Prandtl-Grauert, and also boundary layer model. Okay. That's the way you need to understand. So those are the kind of thing, hopefully you can get it by going through this D3 notes. Okay, so this is xFlyer 5, just introduction to it. And also you have given guideline. This is a more detailed document, which is how many pages? I don't know, quite a bit pages. 58 pages. This actually talks about some in-depth theory too. Okay, so try to understand that. Okay, that is project 3A. You don't have to wait until the last minute for that. Someone else is also raising hand. Dylan, go ahead. Dylan, go ahead.
Yeah, can you hear me?
Yeah, I can hear. Go ahead.
Okay. So I saw in the updates when everything, or in the updates when everything is due. When are we going to be doing the notes for each of these?
Notes.
Are we going to finish the notes for each one, going through all the notes?
Yeah. No, notes means you mean lecture?
Yeah. Like
lecture
will we
is gonna
finish going through?
Yeah, lecture is gonna keep on going. Today I'm going to do unit C1 lecture, and then today is all online. So I'm going to actually thinking of recording entire lecture C1 and put it online so that as you come back from Thanksgiving, we're gonna start lecture of C2. And then probably two classes for C2, and then the rest of the class is gonna be D1, and then maybe one half day for a presentation of xFlyer 5 special project team. That's what I'm thinking. So yeah, I think we can finish up all the material to do those. Am I answering your question? I hope.
Yeah, you are. I was just wondering if you have enough time to do all the lectures.
Yeah, I think we have enough time, but I think you have to realize there are certain contents that you have to do it. So unit C3 panel method. This is YouTube video lecture. You don't have to wait for me for that. This is unit D3 again, YouTube lecture. Actually, no, this is not YouTube, but this is again self-learning material. C4 and D2, those are optional, so I'm not going to cover. This is not going to show up on exam. Okay. So there are a few things that you really need to do it by yourself, so don't wait until last minute for that. Okay. Any other question? Okay, so let's talk about final exam. Final exam is going to be, this is a section 3, so your final exam will be Monday, December 13th, okay? 12:30 to 2:30. Location is King 126. That's just a regular classroom. This is the units covered, 2 hours, 7 programs, very similar style. Again, I do nothing special. All the problems will be taken almost straight out of your notes, lecture notes, homework and quiz and midterm exams. You have to comprehensively cover all of those things. Okay. Any question about final exam? You can do it, of course. I mean, if you've been doing consistently what you need to be doing, this is nothing to worry about. Okay. All right, so let's just get into the unit C1. All right, so unit C1, I'm going to probably take the record of whatever the remaining lecture which I cannot cover online today. I'm going to make up an entire video of unit C1 lecture anyways, so that you can take a look at it. Okay, so after, like I said, after the Thanksgiving, we are going to start talking about unit C2. So unit C1 is 2D airfoil, things that you already know, sort of. So this is nomenclature, okay? So obviously, we are talking about airfoil, which is the cross-section of a wing. This is airfoil. Now, in theory, airfoil is considered to be like, if you think about a wing of infinite span. There's no such a thing, but you can imagine infinite span wing. And then this infinite span wing has a constant cross-section, okay? It's very same cross-section throughout, stretching out to infinity. Then you are going to introduce a cut, which is a unit span cut. Unit span is 1, okay? It could be 1 meter, 1 inch, 1 foot, anything's fine depending on the unit system you're dealing with, but this is called unit span, okay? Unit span. And then you are going to pick up as an airfoil, okay? That's the airfoil by definition. So this is a constant cross-section unit span wing. And then essentially represent a unique cross-section of a wing. In other words, later on the project 3B, you're trying to kind of pick up the software, trying to design your airplane wing. Airplane wing is made up by a choice of cross-section at each unique cross-section at per unit span. In other words, if you choose a single shape, you can create the wing, of course. Okay, because your cross-section is all the same. It's sometimes called chocolate bar wing, okay? It's a Hershey bar wing, and the only design parameter you have will be aspect ratio. I guess that's it. But you can create your own wing introducing different shape. Okay, I'm going to change the root and tip section different shape, and then continuously connect up nicely. You can design such a thing if you're given 2 unique cross-section as a database, the behavior of each airfoil. That is something you have to deal with. So every design, you are going to start with 2D analysis. Suppose if you choose to use 2 different kinds of airfoil, you're going to analyze both of them and understand the behavior. And then, and only then, using those databases to design 3D wing. That's always the process. Okay. So if you take a look at the materials of this unit D3, okay? So if you go through step-by-step process of example of how to use X-Flyer 5, you always begin with cross-section, which is airfoil. So you're going to choose the type of airfoil, then you analyze it and build the database. That is the complete behavior of how this airfoil cross-section behaves. Then and only then, let's use this to create a wing. That is where? Rectangular wing. Okay, if you do not have a database built for this particular cross-section, you can never design anything, okay? So that's quite important. So you always have to run 2D simulations, understand the behavior of a cross-section, which is airfoil, and then and only then utilize that database to design your wing, and then you can predict the wing performance. Okay, you have to properly understand the step-by-step process of how to use this software. Okay, you cannot all of a sudden create the 3D wing, no, because 3D wing is created by 2D airfoil. Okay, so the rest is, of course, you already know some of the detailed nomenclature here. This is a leading edge, obviously, it's given. This is the trailing edge, obviously. So it's like LE, and this is TE. If this is completely symmetric cross-section, you can connect leading edge to trailing edge with straight edge. It's called chord line. Chord. Okay. And then if this is not the symmetric cross-section, oftentimes we call that camber. Camber can be visualized, first of all, defining mean camber line. Mean camber line is upper and lower surface, intermediate point between them. So this is intermediate point between them, upper and lower surface. This is called mean camber line. And then, as you can see, there's a difference between mean camber line and then chord, which is, this is a difference, right? This is a difference between chord and mean camber. This is called the camber. So camber is not a constant value. Camber is 0 at the leading edge. Camber is 0 at the trailing edge. Camber could be maximized at certain locations. So you are oftentimes interested in where is the maximum location of the camber. So in order to describe the camber, you need two things. One is, of course, location of the maximum camber happens. And then what is the value of that maximum camber? That's called description of the entire camber of this airfoil. Okay. So this is obviously cambered airfoil. Now, obviously, we have a positive camber, or we can have a negative camber. Negative camber can be understood as upside down positive cambered airfoil. This is like, have you ever seen this? Like Zach, I guess you know this kind of thing. Where did you use?
On, you know, like wings on cars and stuff for downforce.
That's right, race cars. Race cars rear wing.
Wouldn't it also be for helicopters?
Helicopters.
I'm thinking of like the Huey, which I know has an inverted airfoil on its tail section.
Tail section, right? Ah.
Yeah.
Yeah, okay. Tail section may possibly be. In other words, you have to keep changing the pitch of the tail rotor. Tail rotor may not necessarily be embedded. I have to research. Tail rotor, of course, you have to create a counter-rotating torque against the main rotor shaft. Okay, but again, this is a race car's rear wing. Of course, the purpose is, of course, creating downforce, not the lift. So there's obvious reason why it needs to be embedded. Go ahead.
Is it possible for your chord line to be outside the shape of your airfoil?
Yeah, it could be. Suppose if you create the huge camber like a turbine blade. Okay, so this is like, hey, this is a chord line which is outside of the body itself. Yeah, it can be. But this is usually not the cross section of a wing, though. Okay, unless you stretch out the like high lift devices such as flap. Flap actually does this, creating huge camber temporarily to augment the lift, but at the same time with the sacrifice of increase of lift. We're going to talk about that later, okay? So let's move on here. So this is, once again, definition of lift and drag moment coefficient 3D wing versus 2D airfoil. We talked about that already, okay? So let's move on next page. So we can first of all plot CL and alpha. So this is CL alpha plot, oftentimes called lift curve. We already know this. And then I think we even used it in the past, okay? And oftentimes this is considered fairly linear, not exactly, but fairly linear. If this is a linear, you can define the slope. This is called lift curve slope. We used it. When did we use this to determine what? Somebody please remember this. Do you guys remember midterm exam 2? Problem 1.
Determine X. XCP or X.
No, this is A0,
No, it was
isn't it?
XAC.
This is
for
A0,
center
isn't it?
of,
XAC.
center of
Did you use this A0 for something?
aerodynamic
Yeah,
center.
Aerodynamic
XAC.
center, that's right. So aerodynamic center, that's right.
Yeah, aerodynamic center. That was.
That's right. This is aerodynamic center, okay. So A0 and then M0. M0 is, of course, moment curve slope at the quarter code. And then if it's completely symmetric, this is 0. So that means making aerodynamic center quarter code. Anyways, so remember those things. But this is usually 2 pi per radian. Or if you convert it to per degree, 0.11 per degree. Okay, so that's the value. It's fairly constant. Okay, you cannot really alter this dramatically. Okay, and as you increase your angle of attack, as you can see in this plot, as you increase your angle of attack, you're going to also increase the rift coefficient. So as you pitch up more, you create more rift, of course, but there's a certain limit right here. This is called stall. Now, stall is usually, okay, caused up by flow separation. Flow separates. That actually cause the stall. So flow separation is, of course, creating highly adverse pressure gradient, so the flow cannot follow over the contour. So the flow separates from the surface, and then as it separates from the surface, it just creates the pressure relief. Okay, so that's what we also looked at it. Now, flow separation process may possibly completely be different based on the type of airfoil. So we can compare like a very thin airfoil versus fairly thick airfoil radar so that we can see the difference. The behavior of this stall region is going to be very important when you design airplane. If you do not carefully choose the post stall characteristics, your airplane might possibly be very difficult airplane to handle. But at the same time, you don't want to choose like a very, very thick airfoil for high-speed airplanes, vice versa. Very, very thin airfoil for like an airplane which requires huge internal volume. So it's always a trade-off, but at the same time, the design of the cross-section actually significantly changed the post-stall characteristics too. We're going to take a look at it, okay? Now, X5 can actually predict at a certain extent for this post-stall conditions too. Okay, because the stall is mainly the boundary layer issue. Boundary layer separation is going to determine the characteristics of the post-stall. Of course, X55 can actually come with boundary layer predictions. Okay, as you choose to select to add the boundary layer simulation on top of panel method, so you can actually predict to a certain extent the post-stall characteristics of the airfoil, which is the beauty of this software. Okay. So now, next page. So those are the type of airfoils. This is actually fairly well known. Beechcraft, Sundowner, Bonanza. This is like a classic Beechcraft. It's like a passenger airplane. Those are NACA, well, this is NACA 6 series. Please take a look at handout for that, okay? This is oftentimes called natural laminar flow airfoil. I think I have a handout. Let's just take a look. Yeah. So this is natural laminar flow airfoil NACA 6 series. Okay, so please take a look at it. And then this is NACA 1, 2, 3, 4, 5. This is NACA 5-digit standard. This is NACA 2412. Of course, you know this is NACA 4-digit. So NACA 5-digit, 4-digit, those are called NACA conventional. Okay. Now, what makes the design of airfoil conventional? This is usually aerodynamic center is equal to quarter code. This is what it means. If you put aerodynamic center at the quarter code, actually, no. Sorry. Aerodynamic center is quarter code, period, no matter what. But, okay. Maximum thickness. Maximum thickness is around quarter code location. It's called NACA conventional design. Okay. And then obviously you can choose any cross section to create any design, right? So you can choose to go for like, okay, at the root section, I'm going to choose the same cross section, but at the tip, you're going to change the angle of incidence, which is you're going to twist, physically twist your wing. This is called wash out. Okay. This is, okay, so this is like a root section, and then at the tip, I'm going to increase the angle of incidence of this cross section. This is called wash in. Okay. So those two are physical twists, something called geometric twisting. What?
Professor?
Yeah, go ahead.
Sorry. For the NACA conventional, is the max thickness is the amount of thickness the same as your quarter code length, or is it the max thickness is located at the quarter code length?
Yeah, so this is like a conventional shape. It's cambered, okay? This is a code. So if you take like a quarter code location, that's where you see the maximum thickness. This thing. This is usually called T max. T max is located at quarter code. Now you can choose to shift this maximum thickness location to like a further aft, making like a, let's say half code length is a maximum thickness location. That's called NACA 6 series, natural laminar flow. So it distinctively looks different. Okay. But this looks like a regular airplane cross section, isn't it? Like a quarter code is maximum thickness point kind of thing. So that's called conventional.
I was just confused. I was confused if you meant it was at the quarter code or if it.
Yeah, let's say at the quarter code. Yeah. Okay. And also you can actually choose to have same exact shape, not the same exact shape. You can choose not to change the angle of incidence from root to tip. However, you choose to go for like a different kind of shape. You're going to use root section NACA 6 series, and then you're going to use tip section NACA 4-digit, maybe, for example. Okay. So you are not changing physical angle of attack. However, at the same time, you keep changing the shape. This is called aerodynamically twisting your wing. You can combine those two things all together to design your cross-section of a wing. Okay. So here is some techniques to choose to design your wing. Okay, using X-Flyer 5. X-Flyer 5 can allow you both. Okay. Now, of course, the choice of airfoil is going to have a major impact. So let's just begin with the difference between cambered versus symmetric airfoil. So this is the symmetric airfoil. Obviously, this is the chord line is equal to mean camber line. This airfoil creating zero lift at the angle of attack equal to 0. Obviously, if you do not pitch up, you're not going to create the lift. As you pitch up, lift increases. That's what it is. Okay. Now, if you put the camber, what is the immediate result? You are going to actually create lift, even though you are not pitching up at all. Because of the amount of camber, you already create the lift at the 0 angle of attack. That's this thing. So in order to have a 0 lift for the cambered airfoil, this is, by the way, positively cambered airfoil. Positively cambered airfoil need to pitch down to have a 0 lift. That is called alpha 0 lift right here. This is called 0 lift angle of attack. By putting the camber, this is something you are going to create. That means typically by just putting the camber, you're not going to increase the maximum lift coefficient. But the entire curve is going to be slided to the left. That's what the camber, positive camber. Okay. What it does is the following. So let's say for symmetric airfoil for this much angle of attack, it is going to corresponding to this much lift coefficient. For the cambered, positively cambered airfoil with the same amount of angle of attack, you are now, okay, creating higher value of CL, right? That's what it is, okay? But the whole thing is only shifted, so typically the maximum lift coefficient, CL max, and then CL max, maximum value is not really changed, okay? So you have to be very careful about that. This is called positive camber. Now, can you imagine negative camber, which is upside down flight? What happens? Negative camber. Let's think about that. Positive camber shift the whole thing to the left. What happens to the negative camber? Shift it to the right.
To the right.
That's right. You're right. You guessed it right. So this happens. So this is negative camber. So this is upside down, positively cambered airfoil. Okay. So if it's negatively cambered, now with the same angle of attack, you only produce this much lift coefficient. Okay. So that's what it is. So important thing is lift curve slope A0. This is usually unchanged. By the way, for flight mechanics, this is actually CL alpha. Okay, so this is a CL partial derivative with respect to alpha, CL sub alpha. That's flight mechanics notation you're going to encounter later. And then this is typically 2 pi, especially thin airfoil, it's 2 pi period. And then 0 lift angle of attack, if you put the camber, of course, you have to have 0 lift angle of attack starts to show up. If you put the more positive camber, this is going to be shifted more and more to the left, okay? So that's what you need to be doing. So in order to predict the lift, so this is the linear line. So for a given angle of attack alpha, and then given alpha 0 lift, can I compute the lift coefficient for a given angle of attack? Yes, we can do that. So this is for a given alpha angle of attack, CL is equal to A0, which is typically 2 pi per radian or 0.11 per degree, alpha minus alpha 0 lift. This is the equation to predict the lift coefficient for symmetric. Symmetric means alpha 0 lift is 0. So that means CL is equal to A0 alpha. This is symmetric airfoil. Okay. So those two are the equations. Equations actually linear equation that is essentially this line and also this line. This is a CL equal to A0 alpha line. This is a CL equal to A0 minus A0 times alpha minus alpha 0, right? So this is essentially linear equation. You can actually pick it up and use it. So this is CL is equal to A0 alpha minus alpha 0 left. Or if it's symmetric, this is CL is equal to A0 alpha. Okay. Now, having said that, let's just take a look at next page. Okay. Can airplane fly upside down? What do you think?
If the wing is symmetrical.
Well, if it is cambered, do you think you can still fly upside down?
Yeah, but not recommended.
No.
Well, okay. Well, let's find out. Okay, so
Can it
that's
just pitch up?
pitch up more. Yeah, of course. At the inverted flight and pitch up more. Then you can possibly fly. Okay, that's what you're thinking. Okay, so let's imagine yourself. You have a friend, AS major person, airplane pilot. Every little airplane pilot is the elite people of this country. So you make a good friend with one of those people, and then you go and eat lunch at the flight line. Okay, there's a cafe. Okay, you know, like a very weird looking cafe, like a cut off hangar or something. So, anyways, you engage a lunchtime discussion with a bunch of pilots and start talking about this. Okay, well, can airplane fly upside down? Well, of course, sure. You know, don't you know that? I thought you're an engineer kind of thing. So to answer this question, make the following simple calculation. Consider a positively cambered airfoil with zero lift angle of attack, alpha zero lift, minus 3 degrees. Okay. The lift slope of this airfoil, which is A0, 0.11 per degree. Okay. So now you're going to engage this kind of communication. Okay, so suppose, okay, tomorrow is my check ride, all right? So I'm thinking of doing upside down flight of my Cessna 172. Man, it's so cool. So I'm going to do that. So let's calculate. You're an engineer. Okay, calculate me that the lift coefficient, if I do, well, no. Before I go for inverted flight, fall down for a moment, okay? If I go for Cessna 172 right side up flight, well, of course it's a check ride, 10 degrees and 10 degrees angle of attack, okay? Up right side up flight, okay? How much lift coefficient am I producing? Okay, anyways, so per day for right side up, not the right. Which is regular flight, okay? So I'm, okay, so 10 degrees, alpha equal to 10 degrees. How much CL am I producing? Okay, so that's easy. CL is equal to, right, A0 alpha minus alpha 0 left. Wasn't it right? CL equal to A0 alpha minus alpha 0 left. I know alpha is 10 degrees. A0 is 0.11 per degree. Alpha 0 left is minus 3. Okay, gotcha. So you're going to pick up your calculator. Of course, you are an engineer. You always have a calculator in your pocket and then in front of this pilot, AS major guy. Okay, so I'm going to compute it. So yeah, CL, right? A0 is 0.11 per degree. Alpha is 10 degrees. Alpha 0 left is minus 3. Okay, sorry. Then you quickly compute and say, okay, I give you estimated CL is 1.43. Okay, you're producing 1.43 CL. Okay, cool. So now this person starts saying, okay, so suppose tomorrow's check ride, I'm going to try inverted flight. Then you go like, yeah, for inverted. upside down fried. Okay. Oh, okay. And then, okay, so upside down fried, I'm gonna still push my, okay, so upside down, and push down my nose. So that means you're upside down, pitch up. Okay, upside down, pitch up. You push the, okay. Anyways, okay, I'm gonna try 10 degrees. Okay, yeah. So how much is the lift coefficient then? Oh, then you kind of stop and think. What do you think? Anybody?
Is it gonna be like the 1/CL?
Let's think about this way.
Like,
Okay. Yeah. So this is the positive camber. Alpha zero left is -3. Once you make it upside down, it is going to make automatically negative camber, right? So negative camber actually puts you alpha zero left +3. That's probably something you have to think about. So this is alpha zero left for positive camber, which is -3. If you invert it, that is going to automatically make the negative camber. That is going to automatically shift alpha zero left to +3 degrees, not -3, because you're going to shift all the way to the right. Okay, do you agree? Anybody agree about this?
Makes sense.
Makes sense. Okay. So now you know. Okay. So now inverted fried means alpha zero left now is +3 degrees. Oh, okay. Can I use the same equation? Yeah, I think so. So let's just use the same equation with the condition changed. Alpha zero left is +3 degrees now. So CL is equal to, once again, 0.11 per degree. Same equation, 10 minus +3 degrees. Then you can quickly compute. Well, I got 0.77. Then you reply back like, well, you know, tomorrow's check ride. If you do embodied flight with 10 degrees of angle of attack, according to my calculation, CL is only 0.77. Then apparently your pilot friend get really upset and say, what the hell? I want to keep this same thing, 1.43. I need that. So what should I do? That is question C. Okay. So this is a real question to engineer. Okay. So please take it personally. Every single person today show up online, please take this question personally. If I'm the guy, keep saying, hey, tomorrow's check ride, I'm gonna do embodied flight with my I don't know, flight instructor sitting right next to me. I'm gonna do embodied flight, and then I'm gonna pitch up 10 degrees. And then you keep saying you only have 0.77 lift coefficient, and I'm pretty upset and saying I need 1.43. Damn it! What should I do? And what do you say?
Increase the angle of attack.
Oh, okay, okay. So just for, okay. Well, anybody else?
Can't we like go faster if we could?
Go faster. Okay.
Yeah.
So what is the airspeed? That's a quite interesting question. And also, what is your altitude when you do embodied flight like this? So those are the important questions as an engineer, but at the same time, okay. So 5 more minutes. I'm going to pretend like, hey, this is I may possibly be doing. Okay. So if yeah.
I was going to say you need to be at an angle of attack of 20 degrees to achieve the same. Is that right or is that not?
That's just to find out that exact
Okay.
value of angle of attack you need, okay? So I'm going to keep using the same equation, okay? Same equation. So I keep using same equation. CL is equal to A0 alpha minus alpha 0 left. Now this is embodied flight, so alpha 0 left is plus 3 degrees. We know that. So out of here, how much? Okay. Now CL 1.43 we need. Well, he needs. I don't know. We need. So alpha is, well, I'm going to change from this equation. Alpha is CL over A0 plus alpha 0 left. Make sure everything is unit. So this is unit rest. This is per degree. This is degree. So result is degrees. Okay, anyways. So 1.43 lift coefficient. 0.11. This is per degree. Plus 3 degrees is going to get you 16. So suppose if you say in a casual lunchtime meeting, okay, tomorrow's embodied flight, go for 16 degrees. You should be all right. This pilot, well, I don't know, right after the check ride, you may need to attend this pilot's funeral. Sorry for that. Okay, depending on the flight condition and all that. This is a suicide maneuver. What? So you have to think about it, okay? So today we're going to stop here, but the rest of the unit C1, I'm going to probably do a recorded lecture and then find out why this is bad. Okay, let's find out why this is so bad. But we're going to find out, okay? Do you have any question? Okay, have a wonderful Thanksgiving, okay? Then as you come back from Thanksgiving, we are going to start from unit C2, okay? Have happy Thanksgiving.
You as well. Thank you.
Yep, thank you.
Happy Thanksgiving.
Yep, you too.